Good afternoon. My name is Marie Rienzo, and I want to welcome you to the NIH Office of Disease Prevention's Methods Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and support the development of better methods. Before I begin, I have some housekeeping items. You can submit questions during the webinar by clicking on the question mark in the WebEx toolbar. Please direct your questions to all panelists. We will open the floor to questions that have been submitted via WebEx at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in approximately 1 week. You will receive an email when they are available. Lastly, we would appreciate your feedback about today's webinar. Upon closing the WebEx meeting, you will be prompted to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, Marie. Today's speaker is Dr. Stephen Mooney, Acting Assistant Professor in the Department of Epidemiology at the University of Washington, Seattle. He has a professional background as a computer programmer and recently obtained his PhD in epidemiology from Columbia University. His research focuses on how urban environments shape health, particularly through active transport and transport-related injury, and on developing methods to measure those urban environments accurately. His current research project is focused on building and validating the automatic context measurement tool, an environmental analog of the microarray. This tool is used to gather a standardized set of environmental measures for any location in the United States. It's my pleasure to welcome Dr. Stephen Mooney.
Thank you, Dr. Murray. I'm going to be talking about open data and place-based research, getting the measures we need to ask the right questions. I want to verify that my screen is shared properly. It looks like maybe it's not. How about, is it shared properly now? Okay, great. So going back to sort of to introduce myself a little bit separately, I think everything Dr. Murray said is accurate. I just want to highlight that having been a computer programmer gives me a certain sort of bias on how I think about problems that's going to come throughout the framing of this talk. So I sort of misspent my youth, the first 12 years out of college as a computer programmer. And that gave me some skills, but also gave me sort of an outlook that I think is playing out through my graduate and academic career. So the topical context for today's talk is going to be measuring place. And so we know that there are place-based effects. We know there's place-based correlation in things. You've probably seen obesity maps like the one shown here, where states that are marked darker red have higher obesity rates. And it's a key prevention question to understand whether there's some environmental aspect in the state or some population aspect in the state, something about the people who are there, something about the place that drives these kind of trends. And these place-based effects exist at smaller scale. This is a similar obesity map for Seattle, Washington, where I'm based, and its environment. Similarly, here darker blue is higher population levels of obesity. Similarly, there's sort of spatial clustering of places where people are more obese, places where people are less obese. And to understand whether there are place-based features or whether there are things about the people who live in those places that are driving these trends, or some of both, we really need good measures of place. And so that's sort of the motivation for a lot of the work that I've done. In this case, it's obesity, but there are a lot of outcomes for which there is place-based clustering, and place-based measures can help us figure this out. So broadly, the talk that I'm going to give today, I'm going to talk a little bit about what I'm calling an informatic approach to doing epidemiology, kind of trying to take programming as a tool and use it in the context of getting measures and using those measures. I'm going to give 2 case studies of this, one constructing a measure from data that wasn't originally collected with the intention of measuring the environment, and then a case study in sort of what you can do when you have lots of measures. And I'm hoping these will spur ideas in ways that anybody watching this may want to do research on prevention to sort of illustrate these two steps in the method. Finally, I'm going to close with some conclusions and some next steps here. So the informatic approach is sort of formally informatics is the science of information and information processing. But what I mean here is that that the ways in which we use algorithms in research affect both the data we observe and the questions we ask of the data we observe, and that sort of frames how we do informatic-based work. So when you're working with doing something, if you have something like data collection, which you're used to having people do, and you switch to having an algorithm do it, you get certain benefits. Algorithms compared to people are fast, they're scalable, meaning they can take a lot of data and process all of it, but they're also sadly lacking in common sense. And it's the sort of lacking in common sense part that I want to focus in on for a moment. So the key, I would say, to working with algorithms is that you have to add your common sense to their speed and scalability to get the right answer. And so the amount of understanding you need of an algorithm is not enough necessarily. You don't necessarily need to know exactly how it works. You need to understand where it might diverge from what your sort of what a person's common sense would be on saying what the algorithm is doing. Obviously, the more you know, the better. But this sort of understanding what's actually happening under the hood is a matter of preventing yourself from making large mistakes by automating something that you wouldn't want to automate, or where the automation adds a source of error that you would be able to avoid using your own brain. So why are people doing these kind of informatics-based approaches now? I think the key is that it's a lot easier to make more data when you don't have to code it by hand. So if you think about what you would do if you survey people, if you ask a bunch of people a bunch of questions, you have to record what they answered to each of them. To the extent that we now have technologies and algorithms processing data, collating data, that's generating data for us without the human intervention. And I would argue that that's what big data sort of means. This hype that's around this idea of big data, I think, largely has to do with using code to do things that you would previously have done by hand. So in epidemiology, broadly, I think there are 5 main categories of big data. So things like omic data, things like whole exome sequencing or metabolomics, geospatial data, which I'm going to talk about a little bit here in terms of taking an environmental measure or a ton of environmental measures and linking them to some data that you already have, environmental or electronic health record data, records from a healthcare system is another common sort of framing on big data. Personal monitoring, so like a Fitbit or a GPS and accelerometer, another sort of form of big data. But in certain ways, the most interesting is what I'm calling effluent data, and that's data that wasn't originally gathered or developed with the intention of doing research with it, but which can be reformed into something that you can use to do research. And so my first case study is going to focus on use of effluent data to profile a neighborhood. So this is the case study in constructing a neighborhood measure from effluent data. So the first half of this talk. So the measure in question is going to be measuring physical disorder. And if you're not familiar with physical disorder, there's this concept of broken windows policing that may make it familiar. This idea that if you prevent signs of neighborhood deterioration or of disorder, broken windows and that sort of thing in a neighborhood, that can change norms in ways that will prevent violent crime. And this idea was introduced popularly in a popular press article written in 1982, and famously Rudy Giuliani took it on as first police chief and later mayor of New York City. But there's a problem with the framing, which is that in spite of the fact that so the sort of common story is that Giuliani cleaned up New York and that broken windows policing was effective at preventing violent crime in New York City. But when you dig into the data, you can find that a lot of big cities saw the same decline in violent crime with no broken windows policing policies. And so this is something where, in effect, an environmental measure makes a prediction, the environmental measure being broken windows policing. If it's really effective, you would expect to see bigger drops in crime in places that have broken windows policing. That said, this sort of concept of broken windowsness hasn't stopped being in popular culture, and it's come into health research as well. And so one aspect for it, the one I know best, is this idea that disorder prevents people from outdoor physical activity. So in walk-along interviews with older adults, you see things like poor street lighting would prevent me from walking in the evening, overgrown bushes, shrubs. Sometimes you have abandoned houses and the shrubbery has gotten out of control. And out-of-control shrubbery is a disincentive to walking. More broadly, a recent review came out showing a couple of different pathways that disorder might affect health, either through sort of this norm violation creating risky behavior, which with negative health outcomes like substance abuse or risky sexual behavior, and also a sort of fear-based mechanism, which is more of the out-of-control shrubbery situation, where fear induced by the disorder causes social retreat, which causes diminished physical activity like walking, or this psychosocial stress or idea that encountering the disorder makes you feel worse in ways that leads to negative stress, mental health consequences, or substance abuse. But in order to sort of assess any of this, to see whether this is a real thing, to see whether intervening on disorders, a broken windows type policy for social or health benefits would be successful, we would need measures of disorder to really sort of take this idea seriously. So in other words, we need an environmental measure. We need to know how much disorder there is in a place. In order to assess the disorder theory, we have to measure the disorder in a location. So one way to do this is through effluent data, is through using the neighborhood infrastructure views that you can collect on Google Street View. So if you're not familiar with it, Google Street View is a product built into Google Maps that has street-level imagery, mostly taken from cars, that looks sort of like this image on the left here of Philadelphia. And so for any location in the city, or for most locations in the city, most street locations in the city, you can get this kind of visual imagery. And the process of measurement with effluent data here is to take the imagery that's on this side and turn it into something sort of more like what we have on the right side here, a map of the city with disorder measured at various spatial locations. Okay, so that's what the case study we're going to walk through here is how do we go from street imagery to physical disorder? So here's where the informatics side comes in. I built an application to collect data from Street View, so it's optimized for a dual monitor setup here. The monitor on the right side showing the Street View imagery, the monitor on the left side showing a bunch of questions. So questions might look sort of like this. Sorry to skip around in the slides. But the question would be, is there graffiti, evidence of graffiti that has been painted over on building signs or walls? And if the auditor who's using the system sees it, they would say yes on this side, or if they saw this image, they would say no. And there are a number of indicators of disorder we could collect. So for example, we can see empty alcohol bottles, we can see poor building maintenance, we can see bars on windows, we can see abandoned buildings, abandoned cars, vacant lots, graffiti, litter, and so on. And so using these indicators, we can take a walk down the street. I'm going to sort of illustrate what Street View looks like in practice by walking down the street in Detroit. You sort of move along it, and as you move along, you might see something like this what you're seeing down here as litter, and so you would indicate yes on that box. Similarly, you might move along and say, oh, there's a vacant lot. And as you walk through the screen, the scene using Street View, you get this view of how much disorder there is. So with a bunch of indicators of things that might be present on a given street, garbage or litter, empty bottles, graffiti, you can back into a scale for a latent level of physical disorder on the street. Now, for the purposes of this talk, I'm not going to go into how you might do that. Suffice it to say that there are latent methods, including, I think I use item response theory, but factor analysis, latent class analysis. There are a number of latent scale building or categorization type of methods that can take these individual indicators and both check that they covary as expected, indicating that there is some latent construct underlying the indicators, and then give estimates given which indicators are present of the latent level of disorder on the street. So this technique here using item response theory, which I'd be happy to talk about. You can ask questions in the Q&A section if you'd like to know more about it. but this kind of idea of building a measure from a bunch of indicators is common in psychosocial type measurements, but we can use it in environmental type measurements as well. So let's say we've audited a bunch of streets in Philadelphia now. We have something like an estimate of the latent level of physical disorder in a bunch of locations. So the third step in this measure building process is to use spatial interpolation tools to estimate what we would have seen had we audited places that we didn't actually audit. And so here in this view of Philadelphia, each dot here represents a place that we audited. The red-green color scale, more red means more disorder. To people who know Philadelphia, this may seem intuitive or it may not. Based on what I know of Philadelphia, I think it seems pretty good. But the interpolation technique is taking a spot that we didn't measure, say this location here, and saying based on what's nearby and based on how much the measures covary in general in this space, what would we expect we would have seen in this place had we audited it? And more generally, you can do this with a kind of leave one out cross-validation thing, where you could take something we actually measured and see how wrong we are in predicting it from what's nearby, and get a pretty good estimate of how much spatial error there is in interpolation. So with some interpolation, we can estimate what we would have seen in any of the places that we audited, and we can build maps that sort of look like this that have a good surface layer. And I'll talk in a moment about how we use that to get an individualized estimate. But suffice to say, we now have a measure of disorder throughout the city. There are things we can do to improve those measures, pulling in some ideas from other fields, including air pollution and actually mining, I think, has some interest in this area. These kind of spatial techniques are not limited to health outcomes. So if we use a purely spatial-based interpolation, we see more clustering. If we pull in external data, in this case, housing vacancy rates, which are associated with the kind of abandonment processes that are thought to lead to disorder, we get better estimates of the disorder level at the places that we didn't audit. So empirically, a sort of core question is, does this work well? And one way to look at it is these techniques that we're using the Street View audit to do, similar techniques have been done in person. So here's an example of two audits of the city of Detroit. The first one done in person resulted in the map on the top of this slide. The second done via Street View resulted in the map on the bottom of the slide. Here again, red indicates more disorder. And what I want you to notice is that the same rough areas, I don't know Detroit well enough to know the names of these neighborhoods, but this area and this area were marked as highly disordered in both maps. And like this area up here, this area here, the kind of, I think this is the downtown area, were less disordered overall. And generally, there was a very high correlation between the two measures here. But the in-person audit took approximately 3,000 person hours, and the Canvas audit, the Street View audit, took approximately 100. And so there's back to the sort of point of what algorithms bring you, there is a strong amount of sort of efficiency and scalability that you can get out of using computers to do something that you would otherwise have done in person. So this is kind of the case for using informatics to do measurement, and here that we get sort of roughly what we would have gotten had we done the more person time expensive way. And I want to move on to, so what? So you've got a whole bunch of neighborhood measures. What do you do with that? So there's, once you have a neighborhood measure, you're often interested in how the neighborhood is affecting an actual person. And so often you will compute a location-specific measure for a person. So given someone's street address, you want to geocode it, which I'm going to explain, but which means basically figure out the latitude and longitude for a given address. Then identify the neighborhood around it, say what matters nearby, and then merge the neighborhood with the computed variable. And so in a little more detail, geocoding is the step that says there is some 6100 Executive Boulevard, Rockville, Maryland, which I believe is where the Office of Disease Prevention is located. And you can turn that into this latitude and longitude. Suffice it to say that there's software to do this. I don't have time to go into it, and to be honest, I don't totally understand it. but I think this is a category of where I know enough about the algorithm to know that it is sometimes wrong and that I need to be conscious of where it might be wrong. And fortunately, most geocoders flag where they're uncertain. And so you can use the uncertainty to figure out whether you need to drop certain observations or whether there might be systematic biases owing to less certainty in certain geographic areas. Second, given a location, you need to identify a neighborhood. So taking this blue dot as an example of a location of interest, maybe someone's home address, maybe someone's work address, we need to define some area around it as the neighborhood. And there are a couple of ways to do this, but two of the common ones are to draw a big circle represented here as the green area, saying this is everywhere within, let's say, 1 kilometer of the blue dot. This is called the radial buffer, and it's good for estimating what you might see in proximity to that area. An improvement that takes into account the street grid is saying, starting from here, what are all the places that we could walk to within 1 kilometer? So here, there's a spot, say, up here on this within the green circle, but because of the street grid, there's no way you could get there within 1 kilometer walking. If there happened to be a path through here, maybe you could, but using existing street grid data, we can sort of constrain the 1 kilometer area to the smaller area called the network buffer. The work I'm going to be showing further on here uses network buffers to define the neighborhood. One of the key points about the network buffer is that it takes into account by taking into account the street grid, it changes the amount of area that is accessible from within some distance. And so when you have these street grids, which urban planners tend to think are less conducive to walking, you end up with smaller areas as far as where you can physically get to within a certain walking distance, and that plays out in terms of constraining the neighborhood measure. Finally, I want to mention that 1 kilometer here was an arbitrary size, so you could take multiple different kinds of spaces. You could say, I think one mile is more relevant here. I think half a mile is more relevant. Whatever, it's sort of this is a software thing when you're identifying a neighborhood, and so you can just specify a different size and get a different measure. So finally, given the sort of spatial area, the area that you've defined as being the neighborhood, you can use geographic information system software, GIS software, to compute a value for that same measure in some neighborhood area. So this is a map of physical disorder, the same sort of broken windows concept, made via Google Street View, in this case for New York City. And so zooming in on kind of this North Brooklyn area, if we were looking for a neighborhood where this red area was, sort of draw the circle on the map, sort of conceptually within a program, draw that circle. In practice, there's code doing all of this. We draw the circle and measure the mean value in the area, and that would be the neighborhood measure for a person based right there. So given that we can create these measures, and given that all three of these steps are things that we can write software to do, we have a lot of possibilities for what we can measure. So one of the things I've studied is physical activity, which is thought to be affected by context. You can imagine that certain urban forms encourage walking more than others, and many contextual factors have been studied in reference to physical activity. So at high-level domains, people have looked at socioeconomics, distance to retail or transit, distance to parks, crime and disorder, racial ethnic composition, and so on. I have a long list here with the intent of impressing you on how many things people have studied. And I want to dive into it a little bit more. If we look just at socioeconomics, you could operationalize that as median household income, proportion of households living below the poverty line, maximum educational attainment, mean years of schooling. And so in the end, there are tons and tons of different things you could measure as contextual factors. And so one of the problems of doing good research is to decide which ones we care about. And so I'm making the argument now that one way we can get to it is to sort of draw an analogy with omics research, with genomic type research, and say, why don't we just study all of them? And so taking inspiration from the genome-wide association study, we have what I'm currently calling the Neighborhood Environment-Wide Association Study, or NEWAS, which is basically measure everything we possibly can and then identify which ones are most correlated with the outcome. Obviously, this is a purely correlative type of approach, but causation causes correlation. So we can use that to figure out what the best candidates are for seeing where a change in the environmental exposure causes change in the outcome that we most care about. So I'm going to talk a little bit about a pilot of this kind of approach that I've done previously. Full disclosure, this was my dissertation. So we had data on 3,500 adults, older adults living in New York City in 2011. We had sample weights available to generalize to the older adult population of the city. We had physical activity measured by the physical activity scale for the elderly, which is the self-report scale. The fact that it talks about different types of activity is something I'll get into in a moment. We had self-reported home addresses, and we had 3 waves of data in the data set, but we were only looking at baseline here. So this outcome measure, the physical activity scale for the elderly, is a previously validated 12-item self-report scale that represents past week energy expenditure in a bunch of different activities. It's widely used in research with older adults, and so it includes items for things like walking and home repair and other kinds of things, and I'll talk a little bit more about why this matters. Taking this NIWAS type approach, we looked at 4 outcomes. One, the PACE score, which represents total activity in the past week. Second, gardening. Did you ever garden in the past week? And here's where I want to take a quick aside. When I give this talk, people are often skeptical that gardening happens in New York City, which is fair as far as the media presents it, but I'm going to remind you that New York City has 5 boroughs, only one of which is Manhattan. And so large swaths of Queens and almost all of Staten Island, which are 2 of the 5 boroughs, look like the rest of America, places with lawns and driveways and no sidewalks where you could plausibly garden. A third separate outcome that we can pull out of the PACE scale is walking. So did you walk in the past week or not? And actually also how much, but for the purposes of this analysis, we're looking at any walking versus none. And finally, did you do heavy housework? And that's things where you could work up a sweat inside the house doing chores. So things like vacuuming, for example, counts as heavy housework. And we're using this as a negative control. And I want to spend a little bit of time, especially for a methods talk like this, talking about negative controls, because I think this is an important technique that's underused in epidemiology and prevention research. So negative controls are basically about looking for things where we expect to see no effect. And making sure that we see no effect. So let's say we're interested in whether smoking causes breast cancer. This is not where we're expecting to see no effect. We think smoking may well cause breast cancer. We're concerned about a confounding structure. We know that smoking is associated with drinking, possibly due to some unmeasured factor about people, but we know sort of in the world that people who drink tend to smoke. People who smoke tend to drink more than the rest of the population. We also know that drinking is a cause of breast cancer. And so we're concerned about the confounding owing to drinking and smoking. Let's say we have some measure of drinking, and we think when we control for it, we can fully control the confounding from drinking, but we're not really sure. So we can think about another outcome, in this case, motor vehicle fatality, that we think is caused by drinking. Certainly this idea that drunk drivers crash is a reason to think that drinking causes motor vehicle fatalities, but we don't think it's directly caused by smoking. I mean, with the possible exception of a lit cigarette falling onto your lap while you're driving, in general, smoking doesn't lead to motor vehicle fatalities. So the trick here is if we say, okay, let's see if smoking does predict motor vehicle fatality, or if smoking is associated with motor vehicle fatality in our data after we control for drinking. If it is, then we probably haven't adequately controlled for the confounding structure here. But if it isn't, that's reassuring. It's not perfect. It doesn't mean that we fully control the confounding on breast cancer, but it's a sort of a positive sign. There was a chance that we would have evidence that we hadn't controlled confounding, but if we don't see an association, then we believe we have, at least for that relationship, and if we've controlled confounding for one relationship, we're more likely to have controlled it for the structural factors for another one. So to this sort of in these neighborhood measures, we have 337 measures, and I'll talk about them in a moment, but we don't expect any of them would predict heavy housework. If your urban form or nearby parks or pedestrian safety are affecting whether or not you vacuum, either you're a very unusual individual or more likely there's residual confounding. And so we can use heavy housework as a negative control here to say that we think the things that we're seeing as associated are plausibly causally associated. So neighborhood measures we have about 330 of them, including things like demographics and housing, education, employment and income, urban form. I want to emphasize that these are mostly this is a secondary analysis. This was not funded research. This is my dissertation. And so a lot of these measures were compiled not out of everything that's available, but out of things that were already of researcher interest that were plausibly associated with, largely with walking, so sort of neighborhood measures that are thought to be associated with walking. So I did this analysis two ways. The main one I'm going to talk about today was following the GWAS paradigm, a bivariate regression for each measure independent. So taking each measure and seeing whether it predicts the outcomes of interest like PACE score, heavy housework, and so on. Controlling for individual level effects that we think might be, or individual level covariates that we think might be confounding. I also played with a lasso regression, which is a machine learning technique to select a final set of neighborhood measures automatically. And I'm not going to go into that today, but I'm happy to talk to people more about it if there's interest. And so the question with any of this kind of exploratory approach is, did we actually learn anything? So in bivariate analysis, most neighborhood variables were not significantly associated with total activity. So in the sort of this taking each measure independently and looking at its association, most weren't. So this is a Manhattan plot. If you're not familiar with them, each column here represented by a dot. There's no, the only meaning of the x-axis is the clustering of variables within groups of neighborhood domain assessed. So the green variables here are measures of demographics and household composition. The orange ones are measures of education, employment, and income, which sort of stands in for socioeconomics. Purple are urban form, pink is crime and disorder, and so on. The y-axis represents the negative log 10 of the p-value, or in other words, how strongly predictive the variable is. So anything that's below the bound for any p-value correction is something where we would anticipate that we're not sure based on the data that's there that any association that we see didn't arise by chance. But anything that's above, well, it could be caused by residual confounding. We don't think is purely the sort of sampling due to sampling error plus multiple comparisons. Looking at total activity, we see some associations with socioeconomics, which is not unexpected because generally socioeconomics are strongly predictive of total activity. But then because we have these multiple outcomes, we can look at which measures correspond with which particular outcomes. So we see that the socioeconomics strongly predict gardening, and most other variables don't predict gardening, a little bit of the urban form stuff. Whereas daily walking is predicted by a greater set of these things, and reassuringly, heavy housework is predicted by none of them. So our negative control sort of worked as expected, or as we were hoping it would, to help us believe that we'd controlled some of the structural confounding. So given that we have 330 measures, we can look at which of these specific measures are the ones that came out as statistically significant in this GWAS type analysis. What I mostly want to point out is that they don't make a ton of sense as far as being things you could intervene on easily and immediately improve the activity levels in the neighborhood. So you wouldn't expect that. A lot of them are socioeconomic things like how many people have incomes below half the poverty level or below the poverty line. These are sort of deep and structural things, and maybe not useful to think of from an interventional perspective. They also don't necessarily travel together. So like daily walking was strongly predicted by long travel times, which makes sense, but also by broken windows, which makes less sense. So substantively, the sort of core conclusions here are that are all at the groups of variables levels. Socioeconomic status is related to all types of activity, whereas urban form seems to have stronger connections to walking in particular. Methodologically, I thought the most interesting result was that the results were sort of more interpretable in domains than in specific measures. And this suggests to me that some sort of dimensionality reduction prior to analysis, like a principal component analysis or a factor analysis, might make sense for this kind of approach in the future. That looking at each one individually, there's a lot of noise. I didn't present the results of the lasso regression of the naive machine learning, in part because it was totally uninterpretable. This is a situation where, back to this idea that there is an algorithm and we need to apply common sense to it. In retrospect, I could see that once I looked at the results, I could see why they were so uninterpretable. the overall intercorrelations between these neighborhood measures were so strong that the lasso, which selects individual measures, didn't make a lot of sense. So this is a situation where I think blaming the craftsman rather than the tool, that is, I didn't know enough about what I was doing when I applied this algorithm, is more the right step. I think lasso regression could be useful in some of these contexts, maybe after a principal component analysis. So where are we going with this kind of stuff? There are a couple things I want to point out. First, I'm by no means the only person who's doing informatics in neighborhood measurement. There's a lot of interesting stuff with deep learning and image processing. In principle, you can use it with Street View. This paper, which came out of the Stanford group a little while ago, was using deep learning to identify car types and then using car types to estimate demographic makeups of neighborhoods, which is on the one hand like as stereotyping as could be, and on the other hand seems to work pretty well. This paper is using deep learning to look at satellite imagery, sort of imagery from above. It's not totally clear how to interpret this stuff, but it's fascinating and might be a really good way to get neighborhood measures. On the NEWAS front, I want to acknowledge that Shannon Lynch came up with roughly the same idea. Independently of me, I think of us as kind of the Newton and Leibniz of the NWAS or NEWAS type study, and I think she's doing some methods development in that area as well. There's also a lot of cool stuff going on in a little bit more of a specific place-based kind of thing. There are people working with real-time video to try to detect near misses in traffic, sort of using really advanced image processing to identify objects and how they move around in space, and see whether the pedestrian-like objects and the car-like objects come close to each other, or the car-like objects stop quickly as pedestrians are crossing, which might identify places of greatest risk for traffic conflict. There's also some sort of environmental type stuff using Street View, so like identifying where there are no curb ramps for accessibility issues. And then I also want to mention, this is all sort of focused on image type stuff, but there's also really cool work going on for place-based research using personal monitoring data. So people who ride bikes often use these apps like Strava, which track where they've ridden their bike. And then people are able to use that Strava data to say how much air pollution are bikers actually being exposed to on a day-to-day basis by similarly sort of merging with an air pollution layer, the way that I merged with a physical disorder layer earlier on. So a lot of cool stuff going on in this space, but I kind of want to bring this, remind you that it's not always clear how to interpret this stuff, and the key is that you need to understand what the method is doing enough to know where it's going to diverge from common sense. If you are using Street View to identify a car and using the car to identify the demographics of the neighborhood, you have to think about what it might mean that a car is parked on the street. Does it belong to someone living in the neighborhood? How do you sort of calibrate this stuff? Understanding where your algorithm diverges from what your sort of intuition might be if you were starting from scratch. So in general, like programming is making us more efficient in this kind of stuff. It can dramatically increase our ability to measure aspects of the environment, to use those environmental measures, but we still need to be smart about what those things actually mean. And so that's where I'll stop. I want to mention I didn't include a thanks slide here when I put these together, which was a mistake, but this is not all my work. Andrew Rundle, who was my doctoral advisor, helped a lot with it. Brian Salins, who's my postdoctoral advisor, has helped as well. The whole Canvas team is full of great people. This is definitely a team effort. So thanks for your time, and let's go on to the topic.
Great, thank you very much for that presentation. A number of questions, some specific to some of the materials that you used and methods that you used, and others more general. So this notion of using Google Street View as a way to characterize a neighborhood seems very slick until I stop and think about how often are those street views updated. I drive around Washington, D.C. every day, and neighborhoods change fairly rapidly, and either going into decline or coming out of decline, or maybe going through construction and coming out of construction. If you're relying on that kind of a video record, I think it would be important that it be updated on a regular basis, else you could be getting very outdated data. Do you have any comments on that?
I do. That's a great question. The first thing to know is that Google updates its imagery variably depending on where you are. So there are opportunities for systematic biases there. it updates imagery in urban areas in places where people demand the imagery often, about once a year. So if you're in Washington, D.C., say, especially in places that are changing quickly, if you audit it today, your image is likely to be no more than a year or two old. I have some data that I'm not presenting here because I was literally looking at it this morning before the call, but a group that I'm working with has audited a bunch of streets in New York City, and during the time that we had multiple raters involved, and so we had an inter-rater reliability subsample where the same people rated the same intersections for a bunch of pedestrian safety characteristics, which is not physical disorder, but pedestrian safety. So things like, are there crosswalks, is there street lighting, that kind of stuff. And it turns out that some of the people who we assigned to rate some of the streets, some of the intersections got done faster than others. And so we have sort of by chance inter-rater reliability where the image stayed the same and inter-rater reliability where the image varied. And it actually turns out that for most of the things we were assessing, the inter-rater reliability when things changed was basically the same as when they had varied. So this is, I think the takeaway here is that built environment type infrastructure doesn't change all that fast. And so being, a year out of date is not that big of a deal. But for something like neighborhood abandonment, being 5 years out of date, being 10 years out of date might be a much bigger deal. And I think one needs to be careful about this in general. As an aside, I've been trying to find ways to re-audit neighborhoods that we audited about 10 years ago to see how much things like physical disorder have changed and what the predictors of those changes are. But the right funding mechanism hasn't come along yet. But if you know of it, I would love to hear more.
All right, thank you. What kind of software do you use or is out there for the sort of geocoding that you're doing?
Yeah, that's another great question. So the de facto standard in the field is probably a product made public by a company called Esri, which are the people who make ArcGIS. I can't remember what the name of their geocoder is. It's not free, so that's a downside of it. In practice, I think people often would like to be able to give their addresses to web services, to something like Google. If you type in an address on Google Maps, it will take you to the place on the map, which is a de facto way of geocoding, and it's not hard to write code that uses Google to do your geocoding. That is not a good idea, as it turns out, if the addresses that you're going to pass along are personally identifying information, as they often are if they're home addresses, because typical IRB terms indicate that you won't share that home address with a third party. And so I think in practice there are some people using web-based geocoders, but I think they should not be doing that unless they're sure that they're doing it with not protected information. Certain cities also have their own geocoders. So New York City's Department of City Planning, I think it is, has a product called Lion that geocodes addresses specifically within New York City. And there are tools like that for several cities out there. So if you're doing geocoding within a city, you can use that.
Interesting. We have a couple of questions related to negative controls. As I heard you describe it, I was reminded of work from probably the late 70s, Cook and Campbell, their discussion of time series methods, where they would often recommend including as one of the outcomes a variable that you weren't expecting to change as a function of the intervention that you were trying to evaluate. And if you're include one or more of those along with the outcomes that you think the intervention may affect, and you see the change in the variables that the intervention is supposed to affect, and you don't see a change in the variables the intervention is not supposed to affect, you can make a stronger inference. And it seems like what you were talking about as negative controls is very much the same concept. Is that fair?
That's exactly right. Yes. it's sort of a how much confidence do you have that the thing you're looking at was actually caused by the thing you think it was you were looking at rather than something else. Arguably, like a difference in differences type analysis uses a similar effect when you're looking at a policy change where you use the states or the cities or whatever that didn't get some intervention to account for the time trend. And yeah, that's a little bit more statistical. The negative control is a little bit more conceptual, but yeah, it's very much in that sort of vein of making a more specific hypothesis in order to test it more, to be able to test both the positive things and the negative things. People in lab sciences do this kind of thing all the time, but they have sort of more control over what they're doing. Right? If you want to make sure that your reagent is actually working, you can do something where your reagent should do what it's supposed to do and test that that's actually sort of functioning as it's supposed to, even before you add your other things, what you think you're adding to prevent the reaction or whatever.
You talked about NEWAS, Neighborhood Environment Wide Area Study, I think. And we're comparing it to GWAS studies, which NIH does a lot of, or at least supports a lot of. You have a similar problem in your NEWAS that people have with GWAS, where you're doing lots and lots and lots of tests, and you don't want to be fooled by a bunch of type 1 errors into paying attention to things that aren't real. The figures that you showed had a line, I think it was called Bonferroni line, suggesting that you were using a Bonferroni approach as a way to control type 1 error rate. What are some of the methods that you considered, and did you look at what's being done in the GWAS literature, and is that how you came to use the method that you used? Are there other methods that are possible?
Yeah, that's a great question. In practice, I think I ended up finally using the Benjamin-Hoxburg false discovery rate correction. The images there use the Bonferroni correction because it's a little more familiar and a little more interpretable and a little more conservative, and I didn't want to go overboard on saying what we could figure out with this kind of approach. But I think when I wrote it up, I used the false discovery rate. There's a lot of ongoing work there, and I'm not familiar with the latest in it. I think the best practice is the false discovery rate, which uses kind of a random permutation of possibilities to be slightly less conservative than Bonferroni, which assumes that everything is uncorrelated. I absolutely agree that that's a concern, and in certain ways, I think, as with the GWAS, when you're doing discovery, when you're sort of trying to figure out which candidates you want to follow up on, it's not obvious to me that the absolute value of the p-value is as interesting as the relative value. And one of the things I've been thinking about, this is a very unformed thought, but I've been thinking about whether we should be thinking about discovery as a totally different process where we don't use the same kind of statistics, but instead use sort of a relative ranking, because I think in practice that's what we actually do anyway. And whether there's some better way to quantify, based on the underlying correlations between some things, what might be the best independent techniques to follow up on, or the best independent predictors to follow up on. I am not familiar enough with the more recent stuff in the GWAS and omics literature to know whether other people are looking into this. That's on my to-do list to kind of understand it better. It's a kind of shifty answer, but that's what I got. Does that get at what you were asking about?
Yes. It's always fun to look at how people working in completely different fields are using similar methods, because we often can learn, oh, that's a great trick, I can use that.
Yeah.
So you'll probably have a good time with that investigation. we have a very technical question. Are you willing to share your coding template for automation and analysis in ArcGIS, R, Stata, Python, etc.?
So yes, that's a great question. The thing I'm actually funded to do in this direction is to build an R package to automate calculating neighborhood measurements from census data, and that is very much a work in progress, and I'm hoping to get it out on what's called CRAN, the Comprehensive R Archive Network, the place that you share R packages within a year or two. The idea is that this would be sort of an automatic tool that is comparable to the microarray, where you could plug in a latitude, longitude, and get back computed census measures for any given location, where you could sort of do your own MIWAs or other type of sort of large-scale measurement of a neighborhood for any person. So I'm definitely intending to share that. If someone has a more specific, shorter term, I actually need to do the software engineering, but I said I would do kind of thing, also contact me offline. I'm happy to share code in general. The automatic context measurement tool, this thing I was talking about, is an R package. And actually, eventually, I'd like to make it a web app as well, something where you could plug in the latitude and longitude and download the measures for people who aren't comfortable using R. There, I run into the problem that if the latitude and longitude is personally identifying, then I don't want you to send it to me. And so I think the R package is better for sort of research type studies where the locations might be personally identified. But at any rate, yes, I'm very willing to share, and contact me if you need something right away. And if you're willing to wait for a year or two, I should have something sort of public and documented and a lighter lift to get yourself going available out on the web.
All right. Well, everybody on the call is looking at your email address, so you may hear from some people.
Time the question the right time.
Yeah. What are some good sources for open data about neighborhoods?
That's a great question. So a lot of there are a couple different answers to this. So the bread and butter, as they say, although it recently came to my attention that it should be the beans and rice to have a sort of more global view of things. But sort of the bread and butter, if you will, of neighborhood measurement is clearly the American Community Survey and the U.S. Census. So for social type measures, that's all freely available. It's all easy to download. And it's just a matter of sort of computation to get a personalized measure. For built environment type stuff, for like where are the retail outlets, it's a lot more complicated. There are some, you can issue queries to things like Yelp or whatever to get measures of businesses in different places. I don't know yet that there's a standard, that there's a validated answer for the sort of that built environment type stuff, or other things coming from private industry. And then probably the other really big source for this is a lot of cities have open data portals where they put administrative records online, so it's relatively easy to go out and get all of the records for something potentially arbitrary that a city keeps at the administrative level. So if you're interested in where was the garbage pickup late in the last 2 months, that kind of administrative record might be available on a city's open data portal. And if you can figure out a way to use that in research, that often has spatial data that you can figure out how to use. 311 calls people have been playing with a lot in the literature. That's often through open data portals. There are significant sort of interpretation issues, like does someone calling the government for help really indicate about that neighborhood? Does it indicate they need help? Does it indicate the neighborhood is full of the kind of people who call the government to ask for help? And those kind of one of the big issues with open data is it's of variable quality, and it's there may be sort of conceptual problems in dealing with it, but I think this is where creativity and sort of understanding the processes that get the data out there mean there's a lot of opportunity too if you can figure out how to validate the construct that you care about.
Do you have any advice for people who are interested in doing work related to this, but who don't know the methods well? Do you have any advice on how they can find collaborators?
So that's another great question. I think there are, it depends on what skills they do have and who, where they're, like, what kinds of contacts they have. So I think it's common in my experience talking to epidemiologists to think that if you want to do something with programming, you should go out and find a computer scientist. And I think the reality is that computer scientists are in high demand, particularly around sort of machine learning stuff. And we are not a well enough funded discipline to be able to afford a lot of computer scientist time. And I think training yourself to do some of the programming tasks is probably a better bet than trying to hire someone who can do it for you. I think this is where I'm going to put in a plug that I think this is a real opportunity for some of the NIH's funding mechanisms around training and sort of collaboration building, short courses and the like. But I think some sort of spatial data processing for people in health research would be a great opportunity for this kind of stuff. A hint, hint. Not that it's your space necessarily, so I think there's a certain amount of learning, and then I think in terms of finding collaborators, there are these data science for the social good type institutes within a lot of academic institutions, and a lot of them have the skills but don't have the perspective to ask the right questions, and I think that's where people particularly with a prevention research background, we spend a lot of time trying to figure out what the really meaningful questions are and how to ask them. And I think going to one of those getting involved in that kind of community and understanding what tools they have and kind of looking for the space in the middle of the Venn diagram where your question and their tools really, and the available data is sort of the third piece of that, really come together to make an interesting question answerable, is another good place to go. Those would be sort of my broad recommendations.
One last question. How did you get from computer programming to epidemiology? And as a follow-on, how did you get from Columbia to Seattle?
So let me answer the second one of those first. I got from Columbia to Seattle by design. I spent the first 12 years of my young person life in Seattle and wanted to get back. And so when I was looking for postdocs, I did what I think of as sort of the capture the flag thing of, like, if it looks like you can get to the flag and get back because the flag guard isn't there, go for it, but otherwise wait a little bit longer. I took that approach to finishing my dissertation. When a postdoc came up that was going to be in Seattle working with people I wanted to work with, I ran for it rather than sort of take a little bit longer finishing up my doctorate. Because I knew for various reasons, including sort of personal and social life reasons, and also an appreciation for dark winters, that I wanted to be in Seattle, though ironically it's like beautiful and sunny today, totally ruining the dreary, drab Seattle that I love. But to the first question, to getting from programming to epidemiology, that was driven in part by being sort of driven away from Silicon Valley. I worked with a lot of people I really liked, but the overall sort of gestalt of Silicon Valley was a little bit wearing to me. The sort of idea that technology will solve our problems didn't really get into kind of the structural things that I see as being relevant in the real world. And I kind of wanted to dive into that some more. And then specifically, epidemiology with its sort of interest on causal methods was really sort of abstractly interesting. And I think there's a subset of epidemiologists who were computer programmers at some point in time, and I think there's a similarity to the thinking. Directed acyclic graphs came out of computer science, and the sort of debugging is roughly the same thing as constructing an experiment. There are ways in which the fields are not as disjointed as you might expect. And so I hope that answers the question.
I want to thank you very much.
I just want to add there is a significant pay cut, and so to anybody thinking about going the opposite direction, there is remuneration in technology, and I wouldn't underestimate the value of that. Sorry.
Thank you very much for your presentation and your answers to the questions. I'll turn things back over to Marie.
Thank you, Dr. Marie, and thank you to everyone who participated in today's webinar. As I mentioned at the beginning of the webinar, we will be posting the slides and a recording of today's session on our website next week. You will receive an email with a link to the recording when it is available. Thank you.